Okay, we've looked at simple conditional branches. We've looked at signed branches, or signed comparison jumps. This is a piece of code we're going to do in class. This one's going to have a compound condition. So in this case, note that what we're looking for here, and always read the statement of the problem to find out what your conditions are. So in this case it says, let's write some code that will count the number of 2's that have been entered until 3 2's have been entered or total number of values entered exceeds 10. So that is our stopping condition, okay? That tells us what the termination condition should be. Again, we'll get to that one. We'll flow chart this out. And you know, at this point, we're probably going to stop annotating or doing the design statements and instead flow chart. Again, the reason we're going to do that is when we do the flow chart the right way, we're going to actually minimize jump instructions in code, and we know that's a good thing because when we minimize jump instructions, we're minimizing the hit to the pipeline when we have to dump cache and reload at a new position. Okay, so we looked at signed comparison branches. Now we need to look at unsigned comparison branches, okay? And the reason we have these is because sometimes we have data that by their nature are unsigned. If we have addresses in memory, if I want to compare two addresses in memory, those are unsigned values. If I have characters in the ASCII character set, those are unsigned values. So ages, speed limits, you know, whatever. There are certain types of data that require us to consider the comparison only for unsigned values. So the question is, we have unsigned comparison jumps, but one thing, and I didn't point this out when we were looking at the signed comparison jumps, you'll notice that the mnemonic is fairly similar. We had jump if greater, not greater than or equal. Anyway, we had all of this, and here we need to consider these comparisons as comparisons relative positions on the positive number line, okay? So if all values are considered positive, then jump if above, if the destination is above the source in the comparison, then that jump will execute, okay? Now, here's a thing that we didn't mention before. In fact, I don't even think I said anything about them, is looking at which flags are actually set or cleared, or upon which flags will the jump occur. And the thing I want you to notice here is, wow, it's either one or some combination of the carry flag and the 0 flag. So my question here is, well, I'm not going to talk about Carl Friedrich. Well, we'll just go back and talk about it where we were at. My question here is why no sign flag? Why no overflow flag? Okay? So, and the reason here for the why is sign flag. That doesn't matter. These are all positive numbers. Same for overflow. That's signed overflow. I care about unsigned overflow, and in that case I'm going to be looking at the carry flag. Okay, so as I mentioned, we're not going to, I'll talk a little bit about Carl Friedrich Gauss in class. Very interesting guy. Oh my gosh, prolific in the area of math and the sciences, especially in number theory or areas of mathematics that are relevant to computer science. So we'll talk about him. We'll do a couple more examples. Let's talk real quickly about this. Signed versus unsigned branches. You might think that it's not important to differentiate between the two, and it's actually critical. These two sets of jumps, the signed comparison and then the signed comparison jumps, they test different bits, different status bits in E-flags, and the result is that they can give very different results. So be very careful. If you are comparing data that is unsigned, use the unsigned branches, because they're only going to look at the zero flag and the carry flag. Okay? So be careful. That's my only message to you on that one. All right, so we've looked at several, at this point, we've looked at several examples on branching and looping, looking at compound comparisons or termination conditions. We've noticed that in count-controlled loops that it is a more efficient, fewer operations per iteration of a loop if we use a decrementing count-control loop. And since that is the case, we have a special instruction for count-controlled loops, and it is the loop instruction. So here's the instruction, and here are some of the rules. So statement label must fit in 8 bits. Must fit 8 bits. Okay. Here's the other thing. It's going to look for your loop control or your counter in ECX. So you have no choice about where your counter is going to be. It must be in ECX. Okay? And most important thing, this is the algorithm that it's going to use. It's going to do the following. First thing is it's going to decrement ECX. Then it will check ECX. Okay? If ECX is 0, execution continues with the instruction below. So I'll say we're done. Otherwise, jump to whatever our label is. Okay? So remember this algorithm. The order is important. The first thing is that it does is it decrements ECX. Okay? All right. Because we're going to be using the loop instruction, usually we have, when in count control loops, we have a loop guard, or somewhere we establish a counter and then we check the counter, because if the counter is 0, we don't have to go into the loop at all. We're done. If it's an incrementing count control loop, which we now know we really don't want to do if we can possibly avoid it, then we always compare it to some upper bound to see if we're done. Because we're using ECX as the counter in decrementing count control loops, we have a special jump instruction that guards against the loop counter being 0, and that's jump if ECX is 0. Couple of things to note here. It's doing multiple things, so this is going to be something you want to use before you get into a loop. Don't use it inside a loop. It's a little inefficient. Okay? But it's great for one-time use, which is what you would do with a guard before you get into a loop. All right, let's call it a video with that.